As our last discussion in our fairly lengthy acid-base section, we're going to just spend a couple of slides talking about buffers. Buffers, I've already indicated to you in a titration, solutions that contain both members of a conjugate pair in an appreciable ratio. Now, appreciable ratio, it means between 1 to 10 or 10 to 1. So you've got the conjugate acid and its conjugate base somewhere between 1 to 10 and 10 to 1. Okay, and the thing with the buffer solution is that it makes the solution relatively insensitive to added acid or base. And that's because when we think about what we've got in here, we've got the acid, we've got the base, and we've got quite a bit of both. Now, if you take that and you add some acid to it, what's going to happen is that that acid that you add, the H3O plus, will be neutralized by the existing A minus. So that means that a reaction will go to the left, okay, H3O plus plus A minus, they'll react with each other, okay, because the existing A minus neutralizes the H3O plus. We don't have any H3O plus anymore. We added it, we'd expect a big pH change, but it's gone because we've got enough of the conjugate base in there to neutralize it. Same idea if we add a base, OH minus. If we add a base, then the reaction is going to go to the right, okay, because that base is going to react with some of the existing H3O plus that comes from that HA, okay, so effectively the base reacts with the HA. When the base reacts with HA, it drives the reaction to the right. The existing HA neutralizes the OH minus that you added, and so that OH minus that you added is gone. It's not going to change the pH too much. A way that a student, a fairly average student, but gave me a wonderful insight many years ago into this, was that if you add H3O plus to here, the A minus neutralizes H3O plus but makes HA. So what you're effectively doing is you're turning a strong acid, the H3O plus that you added, into a weak acid, the HA. Same idea if you add strong base, OH minus. That strong base gets neutralized by the HA, making some of the A minus. You've turned a strong base that you added into a weak base, the A minus, the conjugate base in this pair. Ka, of course, for this reaction, H3O plus times A minus divided by HA. Break that up a little bit, so we pull the H3O plus out, take minus the log of everything, and we get pKa minus the log of Ka is pKa, minus the log of H3O plus is pH, and then minus the log of this little thingy here. Rearrange the equation and you get what is known as the Henderson-Hasselbalch equation for describing buffers. The pH of the solution is the pKa minus the log of the Ka plus the log of the ratio of the A minus over the HA. Where you make buffers, you can either do what we saw before, you take a weak acid and partially neutralize it. Every bit of the weak acid you neutralize turns into its conjugate base, or you can do it the other way around. Or you can just mix the weak thing together with its conjugate. Now there's a special buffer that's an ideal buffer, and that's where you've got a 1-to-1 mixture. That actually appears, if you think back to the titration, at the half equivalence point. At the half equivalence point, half the acid is still the acid, the other half has been turned into its conjugate base, and so you got a 1-to-1 mixture. At that, the pH equals the pKa. When you're talking about the acid, of course, you've also got the possibility of having a weak base in the buffer that has a pKb. At that 1-to-1 mixture, at that half equivalence point of a titration, the pH is the pKa, or the pOH equals the pKb. You want to select a buffer pair so that whatever pH you want of the buffer, the pKa of your acid is about equal to that desired pH. Again, we will expand on that in class. All that remains to do is just a little calculation. pH of an aqueous solution that is 0.45 molar HCOOH, that's an acid, and 0.4 molar Na, well that's a spectator ion because it comes from NaOH, it's a spectator ion. And then see HCOO, well that will be minus, that's the conjugate base of HCOOH. Hassel-Bach equation, pH, pKa plus log of A minus over HA. That's where all the values go in, so you get this. Make sure you see that. And the pH is 3.69. Okay. Now, what we have is if we had a 1-to-1 buffer, the pH equals the pKa. So instead of it being 0.45 and 0.4, let's say it's 0.45 and 0.45, or 0.4 and 0.4. The pH equals the pKa. Now in this particular case, Ka 1.8 times 10 to the minus 4. So for the 1-to-1 buffer, the pH would be 3.74. Our buffer here is a little bit more acidic. It's got a little bit more of the acid than the base, so the pH is a little bit less. Do examples of this on the quiz. We'll do examples in class. Hopefully buffers will be easy to you after we have finished all this discussion.